Hello there, and welcome to the Sleepy Space Channel. In the oldest images ever taken of the universe, there are galaxies that should not be there. They sit only a few 100 million years after the beginning, in an age too young to have built them, and yet they shine already bright, already heavy with stars, some already turning as settled disks. A few appear as massive as our own great spiral, though the cosmos had barely begun. Others glow as small red points, whose nature is still uncertain. Tonight, we drift through these impossible early galaxies, and through the quiet ways they may yet be explained. If you find these slow journeys through the universe worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next couple of hours, none of this is anything you need to hold. There is no answer you must reach tonight, and no distance you must cross. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade quietly away. Let's begin. The story we once told about the early universe was a patient one. It began in heat and density beyond anything the present cosmos can hold, a single overwhelming brightness with no room in it for stars or worlds or the empty distances we know. Everything that would ever exist was pressed close together, and there was no darkness anywhere, only a fierce and uniform glare. Then the whole of space began to stretch, and as it stretched, it cooled, and the fierce glare slowly thinned towards something softer and more still. This was the beginning of a long and unhurried unfolding, a story measured not in moments, but in an expanse of time so wide that the mind can only lean toward it and never quite arrive. For a long stretch after that first cooling, the universe held no light of its own at all. The heat had faded, and the particles that had been flying free settled into a thin and even fog of neutral hydrogen, filling all of space without a single flame to break it. Astronomers came to call this quiet interval the Dark Ages, and the name is a plain and honest one. There was no sun in it, no galaxy, no gathered fire, nothing to cast a shadow or warm a surface. There was only the faint and cooling afterglow of the beginning, stretching thinner with every passing age, and a boundless neutral haze waiting in the dark. Nothing moved that could be seen, and nothing burned that could be found, and the whole immensity of space lay wrapped in a plain and even gloom. It was, by any reckoning we might bring to it, an unsettling stillness, a cosmos that had begun in overwhelming brightness and then fallen almost entirely dark. Yet within that darkness, something was quietly at work. The fog was not perfectly even. It carried within it the faintest unevenness, regions where matter lay a little thicker and regions where it lay a little thinner. Gravity does not need light to do its patient labor, and across the long dark, it drew the thicker regions slowly inward upon themselves. Gas gathered where gravity was strongest, and over an expanse of time that resists all ordinary counting, these gathering places grew dense enough and warm enough at their cores to do what nothing in the universe had done before. They began to shine. This was the moment the old story called cosmic dawn, a threshold reached a few 100 million years after the beginning, when the first stars kindled and the long night finally broke. The dawn, in that telling, was a gradual and gentle thing. The earlier stars were expected to be few and scattered, lonely fires in an enormous dark, lighting only the smallest pockets of a cosmos, still overwhelmingly empty. From there, the brightening was meant to unfold in slow and measured stages, one faint fire joined by another, and then another, across ages upon ages. There was nothing hurried in it, and nothing finished. Each new fire was expected to strengthen the light only a little, and the darkness between the fires was expected to yield only slowly, region by region, across ages upon ages. The universe of that early time was imagined as a place still becoming, still assembling its first rough shapes out of the dark, with all its grandeur waiting far ahead in a distant maturity it had not yet reached. Beneath this brightening ran a deeper and unseen architecture. Long before the ordinary matter could gather into stars, another kind of matter had already begun to shape the cosmos from within, a dark and invisible substance that neither shines nor reflects and reveals itself only through the pull of its gravity. This dark matter had drawn itself together first, forming a hidden scaffolding that spread across all of space, a web of unseen wells and ridges laid quietly beneath the visible world. Into these wells, the ordinary gas would fall, drawn down along channels it could not perceive, gathering where the invisible framework had already prepared a place for it. The luminous universe, in this account, was built upon a darker one, and the shape of everything to come was traced first in a matter that gives off no light at all. The building itself was meant to proceed from the bottom upward, and this was perhaps the most settled part of the whole story. Small things came first, and larger things were made from them. Modest clumps of gas and dark matter formed early, and these small clumps drifted and drew together and merged, and from their merging came somewhat larger structures, which in turn merged again. Astronomers gave this slow accumulation the name of hierarchical assembly, and it described a cosmos that grew the way a great structure is raised, one modest piece joined to another across an unhurried span of ages. Galaxies were not thought to arrive whole and ready. They were thought to be gathered gradually out of many smaller beginnings over a course of billions of years. The great orderly forms that fill the sky today were understood to be the end of a long labor, not its opening, and the beginning was expected to hold only the raw and unfinished pieces from which those forms would one day be made. From this patient architecture followed a clear and confident expectation about what the earliest galaxies should look like. They were expected to be small, for they had not yet had the time to gather much. They were expected to be faint, holding only modest numbers of stars in modest bodies of gas. They were expected to be blue, colored by the light of young and newly kindled stars rather than the warmer glow of an aged population. They were expected to be irregular in shape, clumpy and unsettled and rough at the edges, still colliding and merging and finding their form. And they were expected to be low in mass and few in number, sparse points of light scattered thinly through a cosmos that had barely begun to fill. Order and grandeur, the great orderly spirals, and the immense gathered masses were reserved for a later age, arriving only after ages of steady building had done their slow and necessary work. The whole of this expectation rested not on a single glance through a telescope, but on something more considered. It rested on physics, on the known behavior of gas and gravity and light, and on the long, careful reasoning that follows from them. It rested, too, on simulation, on models in which the early cosmos could be set in motion within a machine and allowed to evolve, its gas cooling and gathering and shining according to the rules understood to govern it. From these two foundations, the reasoned physics and the patient simulation, a timeline had been drawn. It marked the dark ages and the first stars and the slow assembly of galaxies, each stage in its expected place, each following gently from the one before. It was a timeline built with genuine care, and for a long while it stood as a coherent and satisfying account of how the cosmos had come to be as it is. There was a real elegance in this picture, a quiet and pleasing order to it. It described a universe that brightened slowly and grew steadily. A cosmos moving without haste, from darkness toward light, from simplicity toward structure, from a scattering of faint young fires toward the grand and settled architecture of the present sky. Each part of it fit against the next, and the whole held together with the kind of coherence that feels almost like truth. The Dark Ages gave way to the first stars, and the first stars gave way to the first small galaxies, and those in turn gave way, across unhurried ages, to the grand and gathered forms of the present. It was the sort of story one could rest within, a long and gentle account of beginnings, unfolding across an expanse of time so wide that its very slowness became a comfort. The early universe, in this telling, was a place still waking, still forming, still finding its way toward the fullness it would only much later attain. And so the earliest cosmos was imagined as a dim and unfinished place, a quiet threshold barely lit, holding only the first faint sparks of everything that was still to come. It was expected to be sparse where the present sky is crowded, small where the present sky is grand, rough where the present sky is ordered, and young in a way that had not yet had time to gather weight or settle into shape. This was the story the models told, and it was a good story, patient and whole and long believed. It was also the story that a new eye on the sky, one built to gather the very oldest light, would soon and gently begin to unsettle. To see the beginning for ourselves, we needed a new kind of eye. The story of a slowly brightening cosmos was built from physics and from careful reasoning. But a story is not the same as a sight. To move from expectation to evidence, we had to gather the actual light of the earliest galaxies and hold it steady long enough to study. That light is faint, almost beyond meaning. It began its journey when the universe was young, and it has been thinning and stretching across the dark ever since. No eye built for ordinary purposes could catch it. So we built an eye for that purpose alone, and we placed it far from the warmth and glow of our own world. The first thing to understand about this new observatory is why it was made to see in colors our eyes cannot. When light travels across an expanding universe, the space it moves through is stretching all the while, and the light stretches with it. A wave that left a young galaxy as ultraviolet or as ordinary visible light does not arrive that way. By the time it reaches us, its journey has drawn it out, shifted it toward the red, and carried it past red altogether into the infrared, into warmth we feel more than see. The oldest light is therefore the reddest and the coolest light of all. To read the beginning, an instrument must be tuned to that long, patient warmth. And so this one was built above all to gather the infrared, the quiet glow of things so distant that their light has been reddening for almost the whole history of time. Seeing in warmth carries a difficulty that shaped the entire design. Warmth is not only what the oldest light becomes, it is also what every warm object gives off, including a telescope itself, and including the world that built it. An instrument meant to detect the faint heat of the early universe cannot itself be warm, or its own glow would drown the very signal it seeks, the way a candle held too close blinds you to the stars. So the great mirror at the center of this observatory is kept extraordinarily cold, colder than almost anything in nature, chilled until its own warmth falls silent and no longer interferes. Only in that profound chill can it listen for the faint heat of the beginning without confusing its own voice for the one it came to hear. Keeping something that cold in the light of a star required distance and shade. The observatory does not circle close above our heads, where the ground and the air and the sun would bathe it in heat. It was carried far out, to a quiet point in space well beyond the moon, where it can hold a steady station in the dark. There it unfolds a great shield, layered and thin, and turns it always toward the sun, so that the star and the bright, warm face of our own world fall forever on one side of the shield, while the mirror and its instruments rest in permanent shadow on the other. On the shaded side, the cold gathers and holds. The telescope keeps the light and heat of home at its back and faces only the darkness, so that the darkness is all it sees. The mirror itself is large, and its size is not vanity, but necessity. To gather light this faint, an eye must be wide, because a wider opening catches more of the few photons that arrive from so far away. A small mirror would let the oldest galaxies slip past unseen, their light too thin to register. So the mirror was made broad, broader than could be launched in a single piece, and was folded for the journey and opened once it reached the dark, unfurling into a single gathering surface. Every part of it bends toward the same purpose, to collect the largest possible share of an almost vanishing light and bring it to a focus where it can be measured. Even with so wide and so cold an eye, the earliest light is too faint to be seized in a glance. This is where patience becomes the true instrument. To find the first galaxies, the observatory does not sweep across the whole sky. Instead, it chooses a single small patch, a piece of the heavens that looks, to a lesser eye, entirely empty, a scrap of darkness with no obvious feature in it at all. And upon that unremarkable spot, it stares and goes on, staring, for a very long time. Hour after hour, the faint light from that patch falls upon the mirror and is gathered, one small grain at a time, until the grains accumulate into an image. This is the method of the long stare, the patient look into a single quiet window, and it is how the faintest things in the universe are coaxed out of the dark. The reason this works is worth resting on, because it turns emptiness into abundance. A patch of sky that seems empty is not empty. It is only faint. The galaxies are there, but their light arrives so slowly that a brief look cannot collect enough of it to form a picture. Given time, though, the light adds up. Each hour brings a little more, and a little more, until shapes begin to emerge from what had seemed like nothing, and the darkness fills quietly with points and smudges of light, each one a gathering of stars, many of them older and farther than anything seen before. What looked like a small window onto nothing becomes a window onto a crowd, and the crowd stretches back and back toward the beginning. To look out into that crowd is to look backward through time, and this is perhaps the strangest gift of the whole enterprise. Light does not arrive instantly. It travels, and travel takes time. The farther away a thing lies, the longer its light has been on its way, and so the older that light is when it reaches us. To see something a great distance off is therefore to see it not as it is now, but as it was when its light departed, long ago. The most distant galaxies in the gathered image are also the youngest we can witness, shown to us as they were when the universe itself was young. By staring far enough into the dark, this observatory does not merely see across space, it sees down the length of time, toward the first light that ever shone. This was the whole purpose for which it was made. It was built to gather the oldest light, to reach back toward the era when the first stars kindled in the cooling gas and the first galaxies began to gather, and to press as near as any instrument has come to the edge of the observable past. It was made to find the beginnings of things, the earliest brightness, the first structures forming out of the long darkness that came before them. It was made to test the patient's story against the evidence, to answer, with real light, the question the models could only imagine. And when the long exposures were finished, and the faint grains had gathered into pictures, the young universe would finally show its own face, no longer a prediction, but a sight. Consider what it means to point such an eye at a scrap of empty-seeming sky and wait. There is no drama in the act itself, only stillness and time. The mirror holds its cold, the shield holds its shade, the station holds far out in the dark, and the light comes in as it will, unhurried, from distances that number in the many billions of years. The observatory asks nothing of the universe but to reveal itself slowly, and the universe answers in the only way it can, one faint photon after another, until the answer accumulates into something we can read. Patience of this kind is a form of listening, and the whole instrument was built to listen well. When at last the young universe came into view, it did not look the way the patient story had promised. The tidy expectation had been of a dim, unfinished place, a scattering of small and faint beginnings, a cosmos only starting to brighten. What the long stare gathered instead was something else, something the old story had not prepared us for. The light was there, as expected, faint and red and ancient. But the shapes it formed, and the number of them, and the weight and order they seemed to carry, would ask us to look again at everything we thought we knew about how it all began. The eye had opened, and the beginning was gazing back. The light this telescope gathers has been traveling for almost the whole age of the universe. It set out when the cosmos was young and small and still finding its shape, and it has been crossing the widening dark ever since. Along the way, whole ages of history have passed. Stars have lived and died, galaxies have gathered and turned, and the space between everything has stretched wider and wider. And still that light kept coming, faint and patient, until at last it fell upon a cold mirror, waiting in the shadow beyond our world. To catch it is to receive a message sent across almost all of time. Looking out into the distance is, in the plainest sense, looking back into the past. Light moves quickly, but it does not move instantly, and space is unimaginably large. When we see the sun, we see it as it was minutes ago, for its light needs that long to reach us. When we see the nearest stars, we see them as they were years ago, and the more distant ones as they were centuries or longer past. Carry that idea outward far enough, and the delay grows to millions and then billions of years. The farther away a thing sits, the further back in time we find it. There is something steadying in this arrangement, once it settles into the mind. No matter how far a galaxy has drifted, its light preserves the moment of its leaving, sealed and unchanging across the whole crossing. The galaxy itself has moved on, aged, perhaps merged with others, or faded entirely in the ages since. But the light in the mirror knows nothing of that later history. It carries only the young galaxy as it was, delivered intact to eyes that could not otherwise have witnessed it. In this sense, distance does not erase the past. It stores the past and hands it forward, one long beam at a time. This is the quiet gift that makes such a telescope possible. It cannot travel to the beginning, and it does not need to. It only has to look far enough into the distance, and the distance itself carries it backward through time. When it turns toward the most remote galaxies it can find, it is not seeing them as they are now. It is seeing them as they were when their light first departed, when the universe was only a small fraction of its present age. In this way, the sky becomes a kind of record, with the nearest pages written recently and the farthest pages written near the very start. Reading those pages calls for a way to measure how far the light has come. The tool for this is the light itself, and the way it has been changed by the long journey. As the universe expands, the space through which light travels expands along with it, and the waves of that light are gently stretched. Light that left a distant galaxy as blue or ultraviolet arrives drawn out and reddened, its color shifted by the swelling of space between there and here. The more the universe has grown since the light set out, the more that light has been stretched, and so the reddening becomes a measure of both distance and time. The most ancient galaxies show this stretching taken to its far extreme. Their light has been drawn so far into the red and beyond that much of it no longer arrives as visible color at all. What began as a young galaxy's warm glow reaches us as infrared, a light too long and too cool for the eye to notice, carried by waves stretched across the entire history of their travel. This is why an instrument built to gather the oldest light must be built to feel the reddest and faintest of it. The earliest galaxies do not shine to us in ordinary colors. They arrive as a whisper at the far red edge of what can be seen. Measuring that stretch, however, can be done with more care or with less. There is a quicker way and a slower, surer way, and both have their place. The quicker way looks at a galaxy's overall color, at how its brightness is spread across a handful of broad bands, from the shorter waves to the longer ones. From the shape of that spread, an estimate of the stretching can be drawn, and with it, an estimate of distance. It is fast, and it can survey many faint smudges of light at once. But it is only an estimate, read from the broad tint of the whole rather than from any single certain mark. The slower way looks instead at the fine detail written within the light. When a galaxy's light is spread out into its full range, like sunlight opened into a band of color, it reveals a pattern of narrow features. Certain elements within the stars and gas absorb or release light at particular, fixed places in that spread, leaving lines that act almost as a signature. These lines sit at known positions when the light is first made. By measuring how far they have all slid toward the red, the true stretch of the light can be read directly, and the distance pinned down with far greater confidence than color alone allows. This slower reading is harder to obtain, for it demands that the faint light be gathered longer and divided more finely until enough arrives to trace those delicate lines. For the most remote galaxies, that can mean staring at a single point for a very long time. Yet it is worth the patience, because it turns a reasonable guess into something much closer to a measurement. The broad color estimate points the way and gathers many candidates quickly. The finer reading of the spread-out light then confirms which of them truly lie at the great distances they seemed to. The earliest galaxies are the hardest of all to pin down, and for reasons that are easy to understand. They are the faintest, because their light has traveled farthest and thinned the most. They are the reddest, pushed to the very edge of what the instrument can detect, and their appearance can be imitated. A nearer galaxy, wrapped in its own dust and reddened by it, can from a distance wear almost the same coloring as a truly ancient one. Seen only through broad bands of color, the two can look alike, a near and dusty galaxy masquerading as a remote and early one. Because of this likeness, the first estimates are treated as claims to be tested rather than facts to be trusted. A promising point of light might at first seem to lie near the very beginning, and then, on a closer and slower reading, prove to sit far nearer and later than it appeared. Some candidates fall away in exactly this manner. Others hold firm and grow more certain the harder they are examined. The work moves carefully, checking each surprising point against the finer evidence, correcting the early numbers, and setting aside the ones that do not survive a second, steadier look. There is a real humility in this process, and it is part of what makes the results trustworthy. Each remarkable galaxy is doubted before it is believed. The false starts are counted honestly, the estimates revised downward or upward as the finer light demands, and the boldest claims held to the strictest test. Only after such care does a distance come to be called confirmed. And when it is, the meaning is quietly extraordinary. A confirmed galaxy at the far edge is one seen as it truly was when the whole universe had counted only a few % of the years it now holds behind it. This slow accumulation of certainty has its own gentle rhythm, unfolding over many nights and many careful measurements. A galaxy noticed in one season becomes a candidate to be gathered again in another, its light divided and studied until the fine lines within it come clear. Only then does the estimate harden into knowledge. It is unhurried work, and it resists the temptation to declare too much too soon. Each remote galaxy earns its place in the records slowly, through repeated looking, until the doubt has been quietly worn away and what remains can be trusted. To hold such a confirmation is to be certain, at last, that a particular smudge of red light is not a nearby imposter, but a genuine window onto the young cosmos. It is a galaxy caught in the act of existing when everything was new, its light having set out across almost the entire span of time to arrive here and be understood. The number attached to it is no longer a hopeful guess. It is a reading, drawn from the fine lines within the light and checked against every doubt that could be raised. Once the distances were confirmed in this way, the surprise waiting in the images could no longer be set aside or explained away as a trick of dusty nearby galaxies. The strange early galaxies were not misplaced or misjudged. They really did lie where they seemed to lie, in the first small fraction of cosmic time, glowing far earlier than the patient old story had led anyone to expect. Whatever puzzles their brightness and their shape would raise, one thing was now settled and certain. The galaxies really were that early, and their light, gathered here after its long crossing, had told the truth about when it began. The first surprise was the simplest one, and in some ways the largest. It did not concern the shape of any single galaxy, or the mass held within it, or the strange color of the light that reached us across the age of the universe. It concerned something far more elementary than any of these. It concerned presence. When the great infrared telescope turned its patient eye toward the earliest stretch of cosmic time, toward a moment expected to be nearly empty, it did not find emptiness. It found light. It found galaxies already there, already shining, already scattered across a sky that the older story had promised would be dark and unfinished and thin. To understand why this counted as a surprise at all, it helps to recall what had been expected. The patient story of the cosmos held that the first galaxies would be few and faint, small gatherings of gas only beginning to warm into starlight. They would be scattered thinly through the young darkness, rare and dim, the earliest sparks of a fire that had barely caught. In that picture, if you turned a powerful eye toward the first few 100 million years after the beginning, you would see almost nothing at all. You would see a handful of faint smudges, perhaps, at the very limit of what could be gathered, and beyond them, a wide and quiet dark. That was the honest expectation, drawn carefully from physics and from the slow arithmetic of how structure was thought to grow. The images told a different story. When astronomers gathered the oldest light from those small, apparently empty patches of sky and drew out the galaxies hidden within them, they found more than the models had prepared them to find. There were more bright galaxies in the early universe than the patient story allowed. Not a few more, at the edge of what might be called ordinary variation, but a plain abundance, a field already populated where a field was expected to be nearly bare. The cosmic dawn, the moment when the darkness first gave way to starlight, appeared to have arrived earlier and more brightly than anyone had thought it would. There is a particular feeling in this kind of discovery, and it is worth resting on for a moment. Imagine pointing the most sensitive instrument ever built toward a place and a time that theory has marked as almost empty. You expect to strain for the faintest signal, to coax a few dim points out of the noise, to celebrate each one as a hard-won rarity. Instead, the field comes back already lit. The galaxies are not hiding at the very edge of possibility. They are simply there, clear and numerous, as though the young universe had been waiting all along to be seen, and had far more to show than the story had promised. The surprise was not a single object that broke a rule. The surprise was the crowd. It was the sense of arriving at a shore, expected to be bare, and finding it already gathered with quiet fires, each one older than almost anything else the eye had ever seen. And the feeling only settled deeper as the counting went on, because the more of the early sky that was gathered, the more of these ancient lamps came into view. These were galaxies shining clearly when the universe was only a few 100 million years old, a small sliver of the 13.8 billion years the cosmos has lived since. To place that in some kind of proportion, the whole of that early stretch amounts to only a few % of the present age of everything. It is the universe in its first youth, long before the sun or the earth, long before most of the elements that make up a living world had been forged in generations of stars. And yet, in that early window, the long exposures showed galaxies already burning brightly enough to be gathered across almost the entire span of cosmic time. Their light had traveled for nearly the whole age of the universe to arrive, faint and reddened, at a single cold mirror far from the Earth, and still it was there to be read. The brightness itself became a puzzle, quiet and persistent. To shine that brightly, that early, a galaxy needs a great deal of light, and light in a galaxy comes almost entirely from stars. So an early galaxy that appears bright must contain either a great many stars gathered with surprising speed, or a smaller number of stars that make their light with unusual efficiency, or perhaps some other engine glowing at its center. Each of these possibilities carries its own weight, and each one presses gently against the patient timeline. To assemble many stars so soon takes more gathering than the slow story seemed to allow. To make light so efficiently asks the young cosmos to work in ways the mature cosmos does not. The very fact of the brightness, before any question of mass or shape, was already asking the old picture to bend. It is worth being careful here about what this brightness does and does not tell us, because the difference will matter as the story goes on. A bright galaxy is not automatically a massive one. Brightness is what reaches the eye, mass is what lies behind it, and the two are not the same. A modest number of very young, very hot stars can pour out an enormous amount of light, while adding up to far less mass than that light might suggest. So the first surprise, for now, is only about the light. It is about how much of it there was, and how early, and how widely it was spread across a sky that should have been dark. The deeper questions of how much matter these galaxies held, and how they came to hold it, belong to the parts of the puzzle still ahead. What made the abundance harder to set aside was the way it deepened rather than faded under scrutiny. When a surprising result first appears, the natural and proper response is caution. Perhaps the count is inflated by a few nearer galaxies, masquerading as ancient ones. Perhaps the sample is small, and a slightly different patch of sky would tell a calmer tale. These are the ordinary corrections of careful science, and they were applied. Yet each deeper look, each longer exposure, each new field of the young sky kept finding more of these early galaxies rather than fewer. The abundance did not thin out as the instruments were pressed harder. It held. And a surprise that holds under pressure is no longer a fluke to be explained away. It becomes a fact to be understood. Consider what it means for a discovery to grow more solid the more closely it is examined. The first bright galaxies might have been dismissed as a happy accident of one small window. But the universe kept offering the same answer from different directions. Turn the great eye toward another quiet patch of the early sky, and again the field came back populated. Gather the light for longer, sift it more finely, confirm the most distant candidates one by one, and the picture only firmed. The early cosmos was not stingy with its galaxies. It was generous with them, more generous than the model had ever asked it to be, and that generosity became one of the steadiest features of the new view. There is something steadying in watching a result grow firmer under care rather than dissolve. Many surprising things in science fade the moment they are questioned closely, and that is as it should be. This one did the opposite. It answered the same way from every direction it was asked, patient and unhurried, until doubt itself began to settle. There is a quiet grandeur in this once the surprise settles into understanding. For a long time, the earliest universe was imagined as a dim and unfinished place, a slow grey dawn barely beginning to brighten. The new images offer a different scene. They show a cosmos that lit its first lamps early and kept lighting them. A young sky already scattered with points of ancient fire when it should have been nearly bare. Nothing here breaks a law of nature. Light still travels as it always has, and gravity still gathers as it always did. What has shifted is only the story of the timing, the sense of how quickly the darkness gave way. And that shift begins not with any exotic object, but with the plainest observation of all. So the first surprise, before mass and before shape, before red dots and quiet galaxies and the giant black holes that would come later, was simply this: the early universe was already lit. Where the patient story had drawn a thin and hesitant dawn, the images returned a sky already glowing, already crowded with galaxies, whose light had crossed almost the whole of time to be seen. It is a modest sentence to hold, and a large one. The cosmos, so young, was not the empty place we had expected. It was awake and full of light, and waiting only for an eye patient enough to gather it in. Brightness was only the beginning of the puzzle. A galaxy can shine for many reasons, and light alone does not tell the whole of what a galaxy is. Behind the glow, there is a question of substance, of how much material has gathered into one place, of how many stars have already been assembled from the raw gas of the early cosmos. When the newest images were studied more closely, that deeper question began to press forward, and it carried a weight that brightness alone could not. Some of the earliest galaxies did not merely look luminous. They looked heavy. They looked, in the reckoning of the astronomers who measured them, as though they held far more stars than the young universe should have been able to build in the time available. The mass of a galaxy is not something one can weigh directly across such enormous distance. It is inferred, patiently, from the light that reaches us, and the inference rests on a simple idea. Stars of different kinds shine with different colors and different strengths, and a population of stars, taken together, produces a combined glow with a particular hue and a particular power. From that combined glow, astronomers work backward toward a number, an estimate of how many stars must be present to produce what is seen. A galaxy full of young, hot stars burns blue and bright. A galaxy weighted toward older, cooler stars leans red and steady. By reading the color and the brightness together, one can translate light into a rough count of stars, and from that count into a mass. When this translation was applied to some of the earliest galaxies, the numbers that emerged were larger than expected, and in a few cases, they were startling. A handful of these distant systems seemed to contain stellar masses comparable to galaxies that had taken most of the age of the universe to grow. The light suggested not a small, unfinished cluster of newborn stars, but something already substantial, already carrying the heft of a mature structure. And this was the difficulty, stated plainly. In the slow story, mass is meant to accumulate gradually. gathered over long stretches of time as smaller pieces fall together. To find great mass so early is to find the end of a long process where only its beginning should be. It is to open a book to the first page and read, already, the closing chapter. The tension lay in the pace of assembly that the old picture allowed. In that picture, galaxies grow from the bottom upward, small clumps of gas and dark matter drawing together, merging and merging again, each collision adding to the whole. This is a process measured in the merging of many pieces across a great span of time, and it has a natural speed limit. There is only so much gas within reach, only so many neighbors to draw in, only so much time in the first few 100 million years for all of it to happen. To reach the mass of a fully grown galaxy, one needs many mergers, and one needs the time in which those mergers can unfold. The earliest galaxies, in this accounting, simply had not lived long enough. There were not enough smaller pieces gathered yet, and there had not been enough time for them to combine. And yet the light said otherwise, or at least it seemed to. This is the point at which honesty becomes essential, because a mass estimate is a delicate thing, built on assumptions that can bend. The number of stars inferred from a galaxy's glow depends on what one assumes about the mixture of stars producing that glow. A few very bright, very young stars can shine with the strength of a great many ordinary ones, and if the eye mistakes such intense brightness for sheer quantity, the mass can be overcounted. Dust woven through a galaxy can redden its light and confuse the reading. Light from other sources, gathered near the center, can swell the total and inflate the apparent mass. Every one of these possibilities loosens the number, and every careful astronomer knows it. The mass estimates carry an uncertainty that does not vanish simply because the figures are dramatic, and that uncertainty will return later in this story, when the puzzle is gently taken apart. Still, the tension was real enough to be worth sitting with, even granting every caution. Even after the estimates were softened, even after the most generous allowances were made for error, some of these early galaxies remained stubbornly heavy. The light that reached us across almost the entire age of the universe still pointed towards structures more massive than the timeline had prepared us to expect. And so the question stood, honest and unhurried. If the mass is truly there, how did it come together so soon? How did the young cosmos gather so many stars into so few places, so early, when the ingredients were meant to be scattered and the assembly meant to be slow? The most extreme of these candidates pressed the question hardest. Among the earliest galaxies, a small number appeared to hold as much stellar mass as our own great spiral holds today, or something approaching it, at a time when the universe was only a small fraction of its present age. To picture this is to picture the finished weight of a mature galaxy already present when the cosmos had barely begun to make galaxies at all. It is as though one looked toward the earliest morning of the universe and found, standing there in the young dark, a structure that by every expectation should have needed the whole of the day to build. These were the outliers, the systems that stretched the numbers to their limit, and precisely because they were so extreme, they drew the most scrutiny and the most doubt. The doubt was healthy, and it deserves to be named clearly rather than brushed aside. It remains entirely possible that some of these masses will shrink as the measurements improve, that a better reading of the light will reveal fewer stars than the first estimates suggested. Faint light that has traveled so far is easy to misjudge, and the history of this kind of measurement is a history of first impressions, later corrected. Every early number is provisional, held loosely, waiting for the next observation to confirm it or gently pull it down. Nothing in this part should be taken as a final verdict. The mass problem is a problem precisely because it is not yet resolved, and the caution that surrounds it is part of its honesty. What the earliest galaxies weigh is still being worked out, patiently, one measurement at a time. And the honest answer for now is that we do not yet fully know. And yet, held with all that care, the finding retains its quiet force. The images had already shown that the early universe was brighter than expected, more populated than the models had allowed. Now they hinted at something further, that this early light might not be thin and newborn, but substantial, backed by real mass, by stars gathered in great number long before the slow story said they could be. Brightness could perhaps be explained by a burst of newborn stars flaring briefly. Mass is harder to explain away, because mass is the accumulated record of stars that have already formed, the tallied weight of a galaxy's whole history to that point. To find great mass so early is to find a long history compressed into a short time. The old story did not forbid this, exactly, but it did not expect it. It had drawn the timeline gently, allowing structure to grow at a measured pace, and this new possibility asked whether that pace had been drawn too slow. Perhaps the young universe assembled its galaxies more quickly than the tidy picture assumed. Perhaps gas turned into stars more readily in that dense, early time, and the pieces came together with a speed the models had not written in. The question was not whether the universe had broken a rule, but whether the rule of slow assembly had been drawn a little too rigidly, and whether the young cosmos had simply worked faster than we thought. If the mass estimates hold, then the young universe assembled great structures with a speed the old story did not expect. The heaviness of these earliest galaxies, should it prove real, would mean that the cosmos was not only lit early but built early, its first galaxies carrying a substance that the slow, patient timeline had reserved for a much later age. The question rests there for now, unhurried and unresolved, waiting for the light to be read more carefully and the numbers to settle. What the early universe weighed, and how it came to weigh so much so soon, remains among the quietest and most patient of the open questions, still turning gently in the dark, still waiting to be understood. Among the strangest of these early findings is a population of small red points of light. They appear scattered through the faintest, oldest images of the young universe, so dim that they might be mistaken for flaws in the picture, so small that they seem at first to be single stars. They are not single stars. Each of these little red dots marks something far away and far back in time, a source of light gathered from the earliest ages of the cosmos, when everything we now see had only begun to take shape. And though they are among the quietest-looking objects in the whole field, they have become some of the most talked about, precisely because no one is yet certain what they are. The first thing to notice about these small red points of light is their color. They glow with a heavy, warm redness, the color of embers rather than the color of a clear blue flame. In the ordinary story of starlight, blue means young and hot, a burst of newborn stars blazing at their brightest, while red means something older, cooler, or dimmed. For an object seen so early in the life of the universe, a strong red color is a small puzzle in itself. It suggests either that these are not what a very young galaxy should look like, or that something is standing between us and their true light, reshaping it before it reaches us. There are several reasons a distant point of light might appear this red, and all of them may be at work at once. The simplest is distance, and the way the universe carries it. As light travels across the growing cosmos, the space it moves through slowly stretches, and the light stretches with it, its color sliding toward the red and beyond. For sources this ancient, that stretching is enormous, so light that may have left as a bright blue glow arrives to us, leaning heavily into the red. Beyond that, there is dust. fine grains of material within a galaxy can absorb the bluer light and let the redder light pass, so that what we finally see is warmed and reddened by the veil it has crossed. And there is age. If a galaxy holds a population of older stars, their combined glow tends toward the red on its own, without any veil at all. Any one of these could account for the color. In these little red dots, it may be some mingling of all three, layered one upon another across almost the whole history of the universe. The next thing to notice is how small they are. In the images, these points of light do not spread out into the soft, extended shape we expect from a galaxy. They stay tight, compact, almost stubbornly, point-like, as though all their light were pouring out from a single, tiny region of space. This compactness is part of what makes them so curious. A great deal of light is coming from a place that appears very small, and that concentration is difficult to explain if we imagine only a loose scatter of ordinary stars spread across a young galaxy. Something in these objects is packed together far more tightly than the gentle, growing systems the old story led us to expect. To gather so much light into so little room, the material within them must be crowded to a degree that the early universe was not thought capable of so soon. It is as though a whole galaxy's worth of brightness had been drawn inward and concentrated to a single warm point, without the spreading arms and soft outer glow that usually mark a settled system. That tightness alone would make these small red points of light worth a second look, even before we consider their color or their number. When astronomers began to count these small red points of light, a further surprise emerged. There were far more of them than anyone had thought to look for. The early universe was supposed to be a thin, unfinished place, and objects this compact and this red were expected to be rare, if they appeared at all. Instead, one long look after another kept turning up more of them, quietly common across the young sky. Their sheer number turns a single oddity into a genuine puzzle, because a rare accident can be set aside, while a whole population must be understood. Whatever these little red dots are, the universe was making them often and early, in a time we had imagined to be nearly empty. So the question becomes what they actually are, and here the honest answer is that we do not yet know. There are a few ideas, and they are not so much rivals as companions, each capturing a piece of what these small red points of light might hold. One possibility is that they are dense knots of stars, an unusually tight gathering of older, redder suns crowded into a small volume, glowing together with the warm color of stellar age. In that reading, a little red dot is a compact galaxy, or the bright core of one, its light dominated by the combined shine of many stars pressed close. Another possibility looks not to the stars, but to what may lie at the center. A growing black hole, feeding on the gas around it, can pour out an extraordinary amount of light as that gas spirals inward and heats. If such a black hole sits at the center of one of these objects, its glow could outshine everything else, filling the tiny point of light with the radiance of material falling in. In that reading, a little red dot is less a crowd of stars than a single bright engine at a galaxy's core, a black hole announcing itself across the whole width of the universe. The redness would then come partly from the stretching of the light across cosmic distance, and partly from dust wrapped around the feeding center, muffling the bluer glow and letting the warmer light escape. It is worth pausing on that image, because it is a strange and quiet one. A black hole, by its nature, gives off no light of its own. It is the darkest thing the universe can make. And yet, when it feeds, the material gathering around it can shine so fiercely that it becomes one of the brightest sources in the sky. In these small red points of light, we may be seeing exactly that paradox in miniature. A darkness so hungry that its surroundings blaze, a hidden weight betrayed only by the heat of what falls toward it. If that is the truth of them, then each little red dot is a young galaxy in the act of growing a giant at its center, caught early while the process was still underway. The most likely answer, as often happens, may be that these two pictures are not truly separate. A single object could hold both a dense gathering of aged stars and a feeding black hole at its core, the light of the two mingling before it ever begins its long journey to us. Then dust and distance would work upon that mingled light, reddening it further, until what arrives is the small, warm point we finally record. In that case, no single description is complete on its own. The little red dots would be composite things, part starlight and part the glow of gas falling inward, wrapped in dust and drawn across the reddening reach of the cosmos, and any honest account of them would have to hold all of those pieces together at once. What makes these objects so valuable, in the end, is not that they are settled, but that they are not. They sit at a meeting point of several of the great questions the early images have raised, touching on how quickly stars could gather, how early black holes could grow, and how much the light we measure can be trusted to tell us what we think it tells us. To understand them fully would be to understand a good deal about the young universe all at once. And so they are studied patiently, their faint light gathered and spread apart, and examined for the subtle fingerprints that might reveal whether stars or a black hole, or both, are doing the shining. For now, the little red dots remain among the most puzzling things in the whole span of the oldest images, and there is a certain calm in admitting so plainly that their nature is still being worked out. They ask nothing of us but attention. They will not change while we consider them. The light we see left them long before there was anyone to wonder about it, and it will go on arriving, faint and warm and patient, whether or not we ever fully explain it. Small, red, and quiet-looking, these points of light hold a great deal of the early universe folded into very little space, and the slow work of reading them has only begun. There is something restful in that thought, that a thing can be genuinely unknown and yet cause no alarm, that a mystery can simply sit in the images and glow. We do not need to solve them tonight. It is enough to know that they are there, gathered from the first ages of the cosmos, small and red and patient, each one a question that arrived to us across almost the entire history of time. They wait in the images tonight, tiny and unresolved, glowing softly at the edge of what we understand, content, it seems, to be looked at for a long while yet, before they give up what they are. Brightness and mass were not the only things arriving ahead of schedule. There was also a quieter surprise waiting in the images, one that took a little longer to notice because it did not announce itself with light. It was a matter of shape. When astronomers looked closely at the forms of these early galaxies, at the way their light was arranged across the sky, they began to see something the old story had not prepared them for. They saw order. Not everywhere, and not in every galaxy, but often enough to matter, and early enough to unsettle. Some of these young galaxies were not the ragged, broken things the model had promised. They looked settled, composed, already gathered into recognizable form. The expectation had been chaos, and for good reason. In the patient story of slow assembly, the earliest galaxies were built from collisions. Small clumps of gas and dark matter fell together, merged, tore at one another, and merged again. A galaxy in that first stretch of cosmic time was supposed to be a construction site, all rubble and motion, lit unevenly by scattered knots of new stars. It should have been lumpy and irregular, pulled into strange asymmetric shapes by the gravity of its neighbors. It should have looked unfinished, because by the logic of the model, it was unfinished. Order, in that picture, was something a galaxy earned slowly, over many turns of its own long clock, after the violence had spent itself and the gas had settled and the shape had finally had time to calm. And yet the images showed calm, arriving early. Among the young galaxies there were disks. A disk is a simple thing to describe and a difficult thing to make. It is a broad, flattened wheel of stars and gas, all lying roughly in one plane, all moving together in the same broad turning. To hold that flat, ordered shape, a galaxy has to have quieted itself. Its material has to have stopped falling inward in random directions and settled instead into a single, shared rotation. That kind of settling was thought to take a long time, billions of years of slow adjustment, because every collision and every infall of fresh gas tends to disturb the disk and thicken it and stir it back toward disorder. To find flattened, orderly disks so soon after the beginning was to find that the stirring had already stopped, or had never been as fierce as the story assumed. The turning itself was part of the surprise. When astronomers measured the motion of gas across some of these early galaxies, they found that one edge was moving toward us and the other edge away, in the smooth, balanced way a spinning wheel moves. That signature is the mark of true rotation, of a galaxy turning as a single ordered body rather than tumbling in a confusion of separate motions. A young galaxy built from recent mergers should not turn cleanly like that. Its parts should still be moving every which way, each carrying the memory of the collision that placed it there. But some of these early galaxies were already turning as coherent disks, their gas circling a common center, their motion patient and organized, as though the galaxy had already decided what shape it meant to keep. The steadiness of that turning mattered as much as the turning itself. A young galaxy still torn by collisions would show ragged, disordered motion, its gas rushing in conflicting directions, and the smoothness astronomers found instead spoke of a body that had quieted its inner weather. It was the difference between a stirred pool and a wheel, between motion that fights itself and motion that agrees. There was more order still, in the finer details. In some of these young disks, astronomers saw the beginnings of structure that we recognize from the mature galaxies near us. They saw hints of spiral arms, those graceful curving lanes where stars and gas gather more densely and shine a little brighter, winding outward from the center. And they saw signs of bars, long straight bridges of stars that cross the middle of a disk and funnel gas inward toward the core. On the great spiral galaxies of the present universe, these features are familiar and beautiful, and they are also understood to be signs of maturity. A bar and a set of spiral arms are patterns that ripple through a disk only after the disk itself exists, only after it has grown stable enough to carry a wave without tearing apart. They were thought to be among the last touches a galaxy adds, ornaments of a settled adulthood, features that take billions of years to emerge and hold. To see even the faint suggestion of such patterns in the young universe was to find adulthood arriving before its time. A bar cannot form in a formless cloud. It needs a disk to run across. A spiral arm cannot wind through chaos. It needs an ordered wheel already turning, stable enough to hold the graceful shape of the wave. So the presence of these features carried a message folded inside it. It said that not only had some early galaxies made disks, but those disks had already grown steady enough and had turned long enough to begin developing the structures we once believed belonged only to the distant future of a galaxy's life. The ornaments of maturity were appearing while the universe itself was still very young. You might picture the difference between the two stories by imagining the same young galaxy twice. In the picture, the old model expected, it is a scattered, glowing smudge, bright in patches and dark between them, its stars strewn without pattern, its whole form still shifting as pieces arrive and collide. In the picture, the image is actually revealed, at least for some galaxies. There is instead a flattened wheel, turning smoothly, brighter toward the middle, perhaps traced with the pale suggestion of arms curling outward, perhaps crossed by a faint central bar. One is a thing in the middle of being assembled. The other is a thing that has, in some real sense, already become itself. And both were supposed to describe entirely different ages of the universe, separated by billions of years. Yet here the finished-looking form was showing up far too near the start. What such order so early implies is a gentler, faster kind of youth than the story had imagined. If galaxies could calm into disks this quickly, then perhaps the early universe was not the endless demolition the model pictured. Perhaps gas could gather and settle and begin to turn as an ordered whole in far less time than anyone expected, the way a spinning cloud finds its plane and flattens into a wheel more readily when it is dense and cool and full of the material it needs. Perhaps the collisions, while real, were not violent enough or frequent enough to keep every young galaxy in ruins. The order in the images did not erase the mergers or the infall or the fierce making of new stars. It simply suggested that a galaxy could pass through all of that and come out the other side, shaped and turning, sooner than the patient story allowed. This is a change in the character of the early cosmos, and not only in its timetable. The old picture had a certain mood to it, a sense of a young universe that was messy and unresolved, all its galaxies caught mid-collision, nothing yet in its final form. The images soften that mood. They show that alongside the chaos, there was already composure, that some galaxies had found their shape while the universe was still counting its first few 100 million years. The youth of the cosmos, in this light, looks less like pure turmoil and more like a place where structure could arrive quickly and hold, where order was not a distant reward but an early possibility, present almost from the start. None of this means every early galaxy was calm, and none of it means the collisions never happened. The universe of that age surely held its share of broken, irregular, colliding things, exactly as the model expected. What the images added was that these were not the only kind. Beside the ragged galaxies, there were settled ones, wheels of stars turning quietly in the young dark, some of them already sketching the patterns of arms and bars we once thought belonged only to the far future. The story had made room for chaos and expected to find nothing else so soon. It had not made room for grace. Order was the last thing the story expected so soon, and yet there it was, already turning in the young dark. Somewhere in those images, a flattened wheel of ancient light circled its center, as it had begun to do when the universe was young, its faint arms curving outward, its slow rotation carried across almost the whole age of the cosmos to reach us. It asks for nothing but patience, and it offers, in return, the quiet suggestion that even in the beginning, the universe knew how to make things whole. Stranger still are the early galaxies that had already gone quiet. Among all the surprises gathered from that young and distant time, this one carries a different weight. The others speak of excess, of too much brightness, and too much mass arriving too soon. This one speaks of something ending. In a handful of the deepest images, there are galaxies that had already stopped making new stars, while the universe was still very young. They are not bright with the blue fire of fresh star birth. They are reddened, settled, and still, the way an old galaxy is still in the present cosmos. And yet the light that carries their stillness left them when the universe had lived only a small fraction of its present age. Astronomers call such galaxies quiescent, a gentle word for a profound change. A quiescent galaxy is one that has largely finished its work of forming stars. Its brightest, hottest, most short-lived stars have already burned through their fuel and faded, leaving behind the cooler, longer-lived, redder stars that linger for ages. In the nearby universe, galaxies like this are common and unremarkable. They are the great smooth ovals of stars we expect to find after many billions of years of slow settling. To find one in the present cosmos is ordinary. To find one so near the beginning is something else entirely, because a galaxy cannot fall silent until it has first lived loudly. Consider what that stillness requires. For a galaxy to appear quiescent so early, it must have formed the bulk of its stars even earlier still, packing a great deal of starbirth into a very short span of time. The old story imagines star formation as a slow and patient accumulation, gas gathering and cooling and collapsing across long stretches of cosmic time. But a galaxy that has already gone quiet in the young universe cannot have grown that way. It must have burned quickly and fiercely, converting its gas into stars in a fast and concentrated episode, and then it must have shut that process down. The stillness we see is not the stillness of something that never woke. It is the stillness that follows an intense and rapid burning. The colors of these galaxies are what first give them away. A galaxy full of young stars glows blue because the hottest and most massive stars are blue, and they burn brightest and die soonest. When those stars are gone and no new ones are forming to replace them, the blue fades, and what remains is the deeper red of the surviving stars, cooler and older and far more patient. A reddened, quiescent galaxy is one from which the blue has drained away. In the young universe, where nearly everything was expected to be forming stars and shining blue, a galaxy already gone red is a signal that its brightest season has passed. The astronomers who study these images read that redness carefully, weighing it against every other explanation, because color alone can be made to mislead. But when the reddening is genuine, it tells of stars that formed long before the light left the galaxy, and of a fire that has since gone out. This is what makes these galaxies feel so strange. They are the mirror image of the other surprises. Elsewhere in these images, the puzzle is one of youth arriving too bright and too soon, galaxies more massive and more luminous than the timeline seemed to allow. Here, the puzzle runs the other way. These galaxies are too old, too soon. They have already passed through the loud, bright phase of their lives and come out the far side into quiet, and they have done so while the universe around them was still in its own first youth. To live fast and fall silent early is a curious thing to ask of a galaxy, and yet the light insists that some of them did exactly that. The question that follows is how a galaxy stops. Star formation, once begun, does not simply exhaust itself and end. A galaxy left to itself, with a steady supply of cool gas, would go on making stars for a very long time. For it to stop, something must change, and astronomers use a single word for that change. They call it quenching, the shutting off of a galaxy's ability to form new stars. Quenching is not one process, but several, and it is one of the quieter, open questions in the study of how galaxies live and change. A galaxy can go quiet in more than one way, and the images alone do not always tell us which way a given galaxy went. One path is the simplest. A galaxy can quench because it has used up its gas. Stars form from cold, dense gas, and a galaxy that turns its gas into stars quickly enough can run its own reserves dry. If the burning is fierce and the resupply of fresh gas is slow, the galaxy exhausts the raw material of star birth and has nothing left to make new stars from. What remains is a population of stars already formed, aging together, cooling together, reddening together. The galaxy is not destroyed. It is simply finished with the making of new light, left to shine with the stars it already has. Another path is more violent, though it too ends in stillness. A galaxy can quench because its gas has been driven out or heated beyond the point where it can gather and collapse. The very stars a galaxy makes can turn against the making of more, their radiation and their winds pushing gas outward, warming it, unsettling it. In the young universe, there was often a growing black hole at a galaxy's center, and such a black hole, feeding on the gas around it, can pour out enormous energy that heats and expels the surrounding material. Whether by the pressure of its own young stars or by the fury of its central engine, a galaxy can lose or warm its gas until that gas can no longer cool into new stars. The result is the same quiet, reached by a rougher road. However it happens, the outcome we observe is a galaxy that has closed its brightest chapter early. And there is something quietly moving in that. These galaxies lived quickly. They gathered their gas, they burned it into stars in a rapid and concentrated season, and then they went still, all while the wider universe was only beginning. If you could stand outside of time and watch, you would see a galaxy flare into brightness and then dim into a settled red glow, its whole loud life compressed into a span that, by the measure of the cosmos as a whole, was very brief. It finished its most vivid work and then simply continued, shining more softly, in a universe that had not yet fully woken. The number of such galaxies matters too. To find even a few of them so early is enough to press on the old story, because the old story did not expect any galaxy to be finished this soon. Each confirmed example is a galaxy that must have formed early, burned fast, and quenched quickly. 3 demands that the patient timeline made difficult to satisfy all at once. And as with the brighter surprises, the honest response is caution as much as wonder. Reading the stillness of a distant galaxy is delicate work. A galaxy can look quiet because its star birth is hidden behind dust, or because the fingerprints in its stretched light have been read too quickly. Some candidates for early quiescence may soften under closer study, revealing a little more star formation than they first seem to show. The truly quiet ones must be confirmed with care, the way the truly distant ones were. Even so, the careful confirmations remain. There do appear to be galaxies that had genuinely stopped forming stars while the universe was young, and their existence widens the puzzle in a direction few expected. It is one thing to imagine the early cosmos building faster than the old story allowed. It is another to find that some of what it built had already grown old. The young universe, it seems, contained not only unexpected brightness and unexpected mass, but unexpected endings, galaxies that had reached the calm of age before the age around them had arrived. There is a kind of symmetry in this that is worth resting on. The early universe was expected to be a place of beginnings alone, dim and unfinished, everything just starting. Instead, the images hold both extremes at once. In the same young dark, there are galaxies blazing into their first light, and galaxies that have already set their brightest light aside. Birth and stillness, the loud and the quiet, arriving together at the dawn of things. The cosmos was not simply switching on. In at least a few places, it had already lived a full and vivid life and moved gently past it. Even stillness, then, arrived early. Some galaxies had finished their brightest work before the cosmos had fully woken, their fires banked, their gas spent or scattered, their red light steady in the young darkness. They rest in the images now as they rested then, quiet and complete, having lived quickly and grown old, in a universe that was still, in every other sense, only beginning. At the center of this puzzle sits another one, heavier, and quieter. It gathers at the very middle of these early galaxies, where the light bends inward and the gas grows crowded. There, in places that had barely had time to assemble a galaxy at all, the images reveal something enormous already in residence. A black hole sits at the core, not modest, not still forming, but grown to a size that seems out of step with everything around it. The galaxy is young, thin, only recently gathered, and yet its central engine is already massive, already anchoring the whole structure with its weight. This is a different kind of surprise than brightness or shape, and it settles more slowly because it touches the question of how the largest single objects in the cosmos come to be. Astronomers have long known that great black holes rest at the centers of large galaxies, including our own. These central giants hold the mass of millions, sometimes billions, of suns, packed into a region from which no light escapes. In the nearby universe, such black holes are woven into the histories of their host galaxies, having grown alongside them across long stretches of time. The two seem to rise together, galaxy and black hole, each shaping the other over billions of years. That slow companionship is part of the old, patient story, and it fit neatly with the idea that everything large took a long while to form. The early universe was not supposed to hold such giants yet. To grow a black hole of tremendous mass, the usual reasoning goes, you begin with something small and let it feed. A single massive star, at the end of its life, collapses under its own gravity and leaves behind a black hole of modest size, perhaps a few times the mass of the Sun, perhaps a little more. From that seed, the black hole grows by drawing in surrounding gas, swallowing matter that spirals toward it, gathering mass across the ages. Given enough time, such a seed can become one of the central giants. The trouble is the phrase "given enough time," because in the early universe there was very little of it to spare. There is a natural limit to how quickly a black hole can feed, and this limit lies at the center of the difficulty. As matter falls toward a black hole, it heats and glows, and that glow pushes outward against the very gas trying to fall in. When the inward pull and the outward push come into balance, the black hole reaches a kind of ceiling on its own appetite. It can grow no faster than this balance allows, because feeding any harder would blow away the fuel before it could be consumed. This ceiling sets a pace, and the pace, while steady, is not swift. To grow from a small stellar seed to a central giant, a black hole feeding at this natural limit needs a great many stretches of time, longer than the young universe had yet lived. This is the shape of what has come to be called the seed problem. If the earliest giant black holes began as ordinary collapsed stars, then even feeding at their fastest sustainable rate, they simply could not have reached such enormous size in the few 100 million years available. The arithmetic does not close. A seed of a few solar masses, doubling on the timescale the physics permits, falls short of 1 billion solar masses by the time the images show these giants already in place. Something is missing from the simple picture, and the missing piece has drawn a great deal of quiet attention. Either the seeds began much larger than a single star could ever leave behind, or the feeding somehow ran faster than the ordinary limit, or the timeline itself needs gentle reconsidering. One answer begins with a heavier starting point. Instead of a small black hole left by a dying star, imagine a great cloud of gas in the early universe, enormous and dense, that collapses directly inward without ever fragmenting into stars at all. Rather than splitting into many small pieces that each become a star, the whole cloud falls together as one, its center growing so concentrated that it collapses straight into a black hole of considerable mass from the very start. Such a beginning would skip the stellar stage entirely, leaving not a seed of a few solar masses, but one of tens of thousands or more. This is the idea of the heavy seed, a black hole born large, and it would give the early giants a great head start. From such a beginning, reaching the sizes seen in the images becomes far less demanding, because the growth would not have to start from almost nothing. The conditions for such direct collapse are particular and delicate. For a great cloud to fall together as a single object, rather than splintering into stars, it must resist cooling and fragmenting along the way. The gas must stay warm enough and smooth enough to hold together as it collapses, which asks for a special corner of the early universe, free of the small, dense clumps that would otherwise seed ordinary stars. Whether such corners were common, or rare, or somewhere in between, is part of what remains to be understood. If heavy seeds formed often, they could explain a whole population of early giants. If they formed only seldom, they might account for the most extreme cases alone, leaving the rest to some other path. The images have made the question pressing, without yet settling which answer holds. There is a further oddity, subtler than sheer size, in the proportion these early black holes keep with their galaxies. In the nearby universe, the mass of a central black hole tends to bear a steady relation to the mass of the stars around it, the black hole holding a small and fairly consistent fraction of the whole. Larger galaxies host larger central black holes, and the ratio between the two stays remarkably even from place to place. This regularity has long been read as a sign that galaxy and black hole grew together, each keeping pace with the other, their fortunes linked across time. It is one of the quiet patterns of the cosmos, a proportion held so widely that it seems to speak of some shared history. In the early universe, that steady proportion appears to be overturned. Some of these young black holes are far larger relative to their host galaxies than the familiar relation would allow. The central giant holds not a small fraction of the surrounding stellar mass, but a startling share of it, as though the black hole had raced ahead while the galaxy around it lagged behind. These are the overmassive black holes, too heavy for their homes, the usual balance between the two inverted. It suggests that in the earliest times, the central engine may have grown first and fastest, gathering its mass before the galaxy had assembled its stars. The companionship of galaxy and black hole, so even in the present, may have begun lopsided, the black hole leading and the galaxy catching up only later. The dense conditions of the young cosmos may help make sense of this early lead. In those first few 100 million years, the universe was far more compact than it is now, its matter packed into a smaller space, its gas denser and more plentiful. A black hole sitting in such a crowded setting would find fuel close at hand, streams of gas flowing inward from every side, feeding it richly and steadily. Where the present universe has thinned and spread, the early one was concentrated, and concentration favors feeding. It is possible, too, that in these crowded early cores, the feeding briefly exceeded the ordinary limit, gas driven inward so forcefully that it outran the outward push for a time. Such rapid episodes, if they occurred, would let the giants grow faster than the steady pace alone would permit. These feeding black holes carry a quiet thread back to the small red points of light seen scattered through the early images. A black hole drawing in gas does not stay dark. The matter spiraling toward it heats until it blazes, and that light can outshine the whole galaxy that holds it. Among the little red dots, some may be exactly this: a growing black hole at the center of a small early galaxy, its infalling gas glowing red through dust and distance, until the point of light is mostly the engine, and only faintly the galaxy around it. If that reading is right, then these dots are not merely curiosities, but views of the early giants in the act of growing, caught while they were still gathering the mass that would make them enormous. The giants at the centers of galaxies were already grown, sitting heavy and dark within galaxies that had scarcely had time to form. Whether they began as heavy seeds born large, or fed faster than we thought the young cosmos allowed, or arose by some combination of paths not yet mapped, remains an open question. The images have shown us that they were there, early and massive, and out of proportion, and that alone reshapes how we think the largest structures in the universe came to be. For now, the black holes rest at the hearts of the first galaxies, grown beyond easy explanation, holding their weight quietly in the young dark while we work, slowly and without hurry, to understand how they grew so large so soon. There are two calm ways the impossibility might soften, and the first begins with how we measure. Before we decide that the young universe broke its own rules, it is worth remembering how much of this story rests on faint light and careful inference. The galaxies in these images are not weighed on a scale, and they are not counted star by star. Their masses and their ages are read from color and brightness, from the way their light is spread across the spectrum, and from a chain of reasonable assumptions laid end to end. Each link in that chain is sound on its own. Yet a long chain, followed across almost the whole width of the universe, can bend in ways that are gentle at every step and surprising at the end. Consider first the simple gap between how bright a thing looks and how much matter it holds. We tend to imagine that a brighter galaxy must be a larger one, packed with more stars, heavier in every sense. That instinct serves us well among the mature galaxies nearby, where light and mass rise together in a familiar rhythm. In the early universe, though, that rhythm can slip. A galaxy's glow is not a direct measure of its mass at all. It is a measure of the light it happens to be making at the moment we catch it. And light, unlike mass, can be produced in sudden, uneven bursts that flare far above what the underlying material would suggest. The clearest way this deceives us involves a small number of very young, very hot stars. Stars of great mass burn with a fierce blue-white intensity, pouring out light thousands of times brighter than the quiet, long-lived stars that make up the bulk of any galaxy. They also live briefly, exhausting themselves in a few million years, a mere flicker against the age of the cosmos. So a galaxy in the throes of a fresh burst of star formation can be crowded, for a short while, with these blazing giants. To an instrument gathering that light, the galaxy looks tremendously bright, and the eye, reaching for the nearest explanation, translates that brightness into a great mass of stars. The truth may be far humbler. A modest galaxy caught in a bright moment can wear the costume of a giant, and only later, when those brilliant stars have burned away, does its ordinary size show through. The difficulty deepens because the young universe seems to have favored exactly such bursts. In a cosmos that dense and that new, gas gathered quickly and lit quickly, and a galaxy could flare into brilliance in a span that, by cosmic reckoning, is almost no time at all. We therefore catch many of these early galaxies not in their settled state, but in the middle of a flourish, when a small mass of gas has just been set alight and shines out of all proportion to what it holds. If we could return a few tens of millions of years later, the same galaxy might have dimmed considerably, its brightest stars spent, its glow fallen back towards something modest and true. But we cannot return. We see each one only in the single moment its light left, and a chance meeting with a galaxy at its brightest will always tempt us to overstate how much lies within it. This is a subtle point, and it is worth resting on. Brightness is a snapshot of the moment. Mass is the slow accumulation of everything that has been built. The two usually travel close together, but in the young, energetic cosmos, they can part company for a time. A handful of luminous newborn stars can outshine 100 million steadier ones, and when they do, any estimate of mass built on that light will read too high. There is a second source of borrowed brightness, and it returns us to those small red points of light that have puzzled us so. Not all of a galaxy's glow need come from stars at all. At the center of many galaxies sits a growing black hole, and as matter spirals inward toward it, that matter is squeezed and heated until it shines with a ferocity beyond any star. When such a center is feeding, its light can rival or overwhelm the light of every star around it. An instrument gathering the total glow of such a place cannot always tell, at first, how much of that glow is starlight and how much is the fire of a feeding core. If we assume it is all starlight, we will imagine a galaxy far more massive than the stars alone could account for. The extra brightness is genuine, but it is not evidence of extra stars. It is the signature of something small and dense and hot, hidden inside, wearing the appearance of a crowded galaxy. Beyond these two, there is the quieter mischief of dust. The space within the galaxy is not perfectly clear. It is threaded with fine grains of dust that scatter and absorb light. And the dust does not treat all colors alike. It lets the redder light pass more easily and holds back the bluer, so that whatever shines through arrives looking redder and dimmer than it truly was. Reddening, this effect is called, and it plays directly upon the very clue we lean on most. When we judge a galaxy's age and mass from its color, a dusty galaxy can masquerade as an old one, its youthful blue light quietly stripped away and reddened by the grains it passed through. The color we read is real, but it has been altered on the journey out, and a reddening that comes from dust can be mistaken for the redness of great age or great distance. Each of these confusions bends the estimate in the same direction, toward more mass and more age than may truly be present. And there is one more assumption, gentler still, that runs beneath them all. To turn a galaxy's lasers into account of its stars, we must first suppose how those stars are distributed by mass, how many small faint ones accompany each large bright one. We usually assume a mixture much like the one we see around us, an ordinary spread of many small stars and a few large ones. But the earliest galaxies may not have kept an ordinary mixture. If the young universe made more of its great, luminous stars than we assumed, then the light we see would come from fewer stars than we counted, and the mass we inferred would shrink. The very brightness that seemed to demand so much matter could be explained by a leaner, hotter population, brilliant beyond its numbers. None of this is a reason to dismiss what the images show. The galaxies are there, early and glowing, and no careful reading makes them vanish. But it does invite a certain patience about their weight and their years. The first estimates of anything faint and far are the roughest, and the history of this work is a history of numbers gently revised as better light arrives and better assumptions replace the earliest guesses. What looked, in a first quick reading of colors, like a galaxy as massive as a mature spiral has, in a slower and surer reading of its spread-out light, sometimes settled into something smaller and more reasonable. The impossibility does not always survive a second, calmer look. This is why the surer measurements matter so much, the ones drawn not from broad color alone, but from the fine fingerprints written across a galaxy's light. Those readings take longer and demand more of the instrument, but they pin down distance and character with a confidence that a quick color estimate cannot offer. As more of the early galaxies are studied this way, the wildest figures tend to ease inward, and the puzzle, without ever disappearing, loses some of its sharpest edges. A galaxy that seemed to hold 10 times too much mass may, on closer study, hold only 2 or 3 times too much, and even that gap may narrow further with time. There is a further caution woven through all of this, and it concerns the false alarms. Not every point of light that looks impossibly early truly is early. A cool, dusty galaxy much nearer to us can, by an unlucky accident of color, imitate the reddened glow of a far more distant one. From a quick reading, the two can look almost the same, and a nearby galaxy in disguise can be mistaken for a witness to the first hundreds of millions of years. Some of the most startling early candidates have, on patient re-examination, proven to be such imposters, ordinary galaxies wearing a distant face. The careful work of separating the truly ancient from the merely dusty quietly trims the list of impossibilities each time it is done. What remains after that winnowing is smaller and steadier than the first excited count, and far more trustworthy for it. Patience, then, is the quiet virtue this whole picture asks of us. The method moves gently against our first excitement, testing each claim, correcting each estimate, and preferring the modest figure that survives a second look to the astonishing one that does not. Every revised number that settles a galaxy into something more ordinary is not a disappointment. It is the reading working as it should, easing an early overstatement back toward the truth. And more than a few of these impossible galaxies have already made that quiet journey, from a first reading that seemed to defy the timeline to a later one that fits within it after all. We are, after all, trying to read the faintest messages the universe has to offer, sent from a time when it was only a few % of its present age, stretched and dimmed and reddened by nearly the whole span of cosmic history before they reach us. It would be strange if our first readings were flawless. Some part of the impossibility, then, may not live in the young cosmos at all. It may live in the difficulty of the reading itself, in the honest, hard work of turning a smear of ancient light into a mass, an age, a story. And there is a quiet comfort in that thought. The universe may not have broken any rule. We may simply be learning, slowly and carefully, how to listen to a light that has traveled almost forever to be seen, and how to correct ourselves as we go. The second way of easing the puzzle looks not at our instruments, but at the early universe itself. Perhaps the young cosmos was simply better at making stars than the patient story assumed. Perhaps the same physics we know still applied, only turned toward a quicker beginning. In this reading, nothing is broken and nothing is forbidden. The rules hold, but the conditions were different, and different conditions can produce a different pace. The early universe was smaller, denser, and closer packed than the one around us now. Gas, that would later be spread thin across enormous distances, was once gathered near, pressed together, ready to fall inward and ignite. And in a place like that, the making of stars may have run faster and reached further than the slow account allowed. Consider first the density of the young cosmos and what it might have meant for the gas within it. In the standard picture, a cloud of gas collapses, and only a modest fraction of it ever becomes stars. Much of the gas resists, warmed and stirred and held apart, so that the yield is low and the building is slow. But in the early universe, the same cloud sat inside a smaller volume, and everything was nearer to everything else. The gas was denser, the gravity wells were tighter, and material that fell inward had less room to scatter and disperse. Under such crowding, a larger share of the gas might have turned into stars before anything could stop it. Where a later cloud gives up only a small portion of itself to starlight, an early cloud might have given far more. That single change, a higher efficiency of star formation, would let the young universe shine brightly, with less raw material and in less time than the tidy timeline expected. To picture the difference, you might imagine two clouds of the same weight, one early and one late. The late cloud is loose and slow to gather. It forms a scattering of stars and holds the rest in reserve. The early cloud is compact and quick to fall. It converts much of itself into starlight, almost at once. Both obey the same gravity and the same chemistry. Yet the early cloud produces a brighter, more populous galaxy far sooner, simply because its gas was denser and its conversion more complete. Nothing has been added to the physics. The universe has only been asked to run its ordinary machinery in a setting that favored speed. And a setting that favors speed is exactly what the crowded early cosmos may have provided. There is a second possibility that deepens this one, and it concerns the very first stars to form. The stars we see today draw on generations of material enriched by those that came before, seeded with the heavier elements forged in earlier stellar lives. But the first stars had no such inheritance. They condensed from gas that held almost nothing but the lightest elements left over from the beginning, hydrogen and helium and little else. Gas that pure cools and collapses in a different way, and the stars it forms may have been unlike any that shine now. Many astronomers suspect that this earliest generation was made of stars far larger than the ones around us today, tens or even hundreds of times the mass of our own sun. And stars of that size behave very differently from the modest, long-lived stars we know. Such stars would have burned with a fierce and enormous brilliance, pouring out light out of all proportion to their number. A single one of them could outshine a whole cluster of ordinary stars, blazing hot and blue and blinding across the young dark. Because they were so massive, they lived only briefly, exhausting their fuel in a small handful of millions of years, rather than the long ages that smaller stars endure. But in that brief and dazzling life, they would have flooded the early universe with light. A young galaxy built partly from stars like these could appear far brighter than its true weight in matter would suggest. It would seem to blaze with the output of a much larger population, when in truth, a few extraordinary stars were doing most of the shining. This first generation, unlike any that shine today, offers another way for the early cosmos to have been bright and swift while obeying every law. These two ideas, the denser gas and the extraordinary first stars, fit together into one gentler account. Star formation may have been more efficient, converting more of each cloud into light, and the stars themselves may have been more luminous, giving more light for each unit of mass. Together, those two shifts could explain a great deal of what the images seem to show. Galaxies could appear more numerous because more of them managed to light up early. They could appear brighter because their stars were hotter and their gas more fully spent. And they could appear to arrive sooner because the whole process of turning gas into starlight simply ran ahead of the slower schedule the old story had drawn. None of this requires a new universe. It requires only that the young one worked a little differently from the mature one we inhabit now. There is a further piece to this, quieter than the rest, and it has to do with what usually slows star formation down. In galaxies today, the making of stars carries within it the seeds of its own restraint. As stars form and live and end, they release energy back into the gas around them, heating it, stirring it, and pushing it away. This return of energy, this feedback, holds much of the gas apart and keeps it from collapsing freely, so that star formation proceeds gently and never runs away. But in the earliest galaxies, that braking force may have been weaker or slower to take hold. There had been fewer generations of stars to enrich and heat the gas, and less time for the restraining energy to build. With less to hold it back, the gas could have fallen inward and formed stars more freely, at least for a while, before feedback caught up and steadied the pace. A young universe with weaker brakes is a young universe that could build quickly, exactly as the images seem to suggest. When these pieces are gathered together, a calm and pleasing picture emerges. The early cosmos need not have violated any principle to appear as bright and busy as it does. It may simply have been a place where gas was dense, where the first stars were enormous and radiant, and where the forces that slow star-making had not yet gathered their full strength. In such a place, the ordinary work of turning gas into light would run faster and reach further than the slow story assumed. The timeline would not shatter under the weight of these findings. It would only loosen, stretching gently to admit a quicker start, the same physics running a touch sooner and a touch stronger than we had written it down. And a timeline that loosens rather than breaks is a comfortable thing, because it keeps the universe lawful while making room for surprise. Beyond all of this lies one more thought, offered softly and held with care. Almost everything in this account rests on assumptions about how the young universe grew and expanded, and about the pace at which time and space unfolded in those first ages. It is worth admitting, quietly, that our understanding of that early expansion is not complete. There are gentle hints, still faint and unresolved, that the very earliest cosmos may have behaved in ways we have not fully mapped, that its growth held subtleties we are only beginning to sense. These are open questions, not answers, and they are offered here as questions and nothing more. It may be that the timeline simply needs a modest loosening within the physics we already know. It may be that something a little deeper waits to be understood about the first moments of the expanding universe. Both remain possible, and neither is asserted, and there is no need to choose between them tonight. What matters, in the end, is how little violence any of this requires. The galaxies that seem too bright and too soon may be telling us that the young universe was fertile and quick, not that it was lawless. Dense gas, turning readily into stars, a first generation blazing with rare brilliance, feedback slow to arrive, a timeline gently stretched, and a soft, unanswered question about the earliest expansion, held open and unforced. These are the calm ways the impossibility softens from within. The young universe may simply have been better and faster at making stars than the neat account supposed. It was not broken, and it did not cheat. It only worked in its own way, in its own crowded and radiant youth, at a pace the slow story had not thought to expect, and the light it made so early is still traveling toward us, patient and unhurried, waiting to be read. It is worth resting for a moment on that word, impossible, and what it really means here. The word carries a weight it may not deserve. When we say a galaxy should not exist, we are not saying the universe has broken one of its own laws. We are saying that the picture we drew of the early cosmos, careful and reasoned as it was, did not leave room for what the images now show. These are two very different statements, and the distance between them is the whole of this story. A law of nature broken would be one thing, and it would be a genuine crisis. A picture that needs redrawing is something else entirely, something far gentler and far more ordinary in the long life of science. Nothing found in those early fields is truly forbidden. No galaxy there defies gravity, or ignores the way light behaves, or violates the physics that governs how gas gathers and how stars ignite. Every one of those galaxies is made of the same matter, obeys the same rules, and shines by the same processes that govern everything we have ever studied. What they defy is not a law, but an expectation. They arrived brighter, heavier, and more settled than the timeline we had sketched allowed for. And a timeline is not a law. A timeline is a story we tell about the order in which things happen, built from the best physics we have and the best simulations we could run. When such a story meets something it did not predict, the story bends. The universe does not. This is the difference that matters most, and it is easy to miss when the word impossible is spoken aloud. There is the universe overturning a rule, and there is our model being drawn too rigidly. The first would be extraordinary and troubling. The second is simply what models do and what they are for. A model is a map, and a map is never the territory. It is a useful simplification, a set of expectations laid over the world so that we can find our way. When the territory turns out to hold a mountain the map did not mark, we do not conclude that the mountain should not be there. We conclude that the map was incomplete, and we begin, patiently, to redraw it. The early galaxies are that unmarked mountain, standing exactly where they stand, indifferent to whether we expected them. Astronomy has walked this path many times before, more times than anyone could easily count. The history of looking upward is, in large part, a history of things that once seemed impossible, slowly becoming ordinary. Again and again, some new instrument or some sharper way of seeing revealed a feature of the cosmos that the understanding of the day could not accommodate. Objects were found where none were thought to belong. Distances turned out to be far greater than anyone had imagined. The universe proved larger, older, and stranger at nearly every turn than the models of the moment had prepared us for. And each time, the same quiet thing happened. The impossibility did not last. It softened, it was studied, and eventually it was folded into a wider understanding that made room for it. What had been a contradiction became, in time, simply a fact, one more piece of how things are. The people who lived through those earlier surprises must have felt something like what we feel now, a mixture of unease and wonder at a cosmos that kept refusing to stay inside its expected shape. Yet they did not stop looking, and their persistence was rewarded. Every wall they met turned out to have a door in it. Every fact that could not be became, with patience, a fact that simply was. We are the inheritors of that long habit of looking, and of the trust it teaches that the sky, however strange, can, in time, be understood. This is perhaps the most reassuring pattern in all of science. Today's impossibility becomes tomorrow's ordinary understanding. The word impossible, in the mouths of those who study the sky, is rarely a wall and almost always a doorway. It marks the boundary of what we currently grasp, and boundaries are precisely where understanding grows. When astronomers first met a puzzle they could not explain, that puzzle did not stay a puzzle forever. It became a question, and the question became a program of work, and the work, carried out over years, dissolved the impossibility into knowledge. The galaxies that trouble us now stand in a very long line of things that once could not be, and later simply were. So it is gentler and truer to hear the word impossible as a kind of shorthand. When we say these galaxies should not exist, what we more precisely mean is that we do not yet fully understand how they came to be so soon. Impossible is the word we reach for when we lack a better one, a placeholder for a mystery we have not yet solved. It is not a verdict on the universe. It is a confession about ourselves, about the edge of our present knowledge, about the point where our careful story runs out and something new begins. And there is no shame in that edge. Every field of knowledge has one, and the edge is where all discovery happens. To stand at it and feel a little unsettled is not failure. It is the ordinary sensation of learning something the world had not yet told us. Consider what these galaxies are actually asking of us once the fear is set aside. They are not asking us to abandon physics, or to believe in anything strange or unfounded. They are asking us to loosen a timeline, to let the early universe be quicker and more productive than we had assumed. They suggest that gas may have turned into stars more readily in that dense young era, that the first structures may have gathered faster, that the cosmos woke and began its work with more speed than the tidy picture allowed. This is not a broken universe. It is a universe that was busier at the beginning than we had thought, more eager to make light, more ready to build. The correction runs entirely in the direction of abundance, not of contradiction. There is nothing frightening in a beginning that made more than we expected. If anything, it is a kinder finding than the one we had prepared for. A young universe that was gentle enough with its own materials to build so freely, so early, in the dark. And so the young cosmos begins to look not wrong, but simply more generous than the story we had written for it. It was fast where we had imagined it slow. It was bright where we had imagined it dim. It was fertile where we had imagined it barren, already growing things in an age we had pictured as empty and dark. None of this makes the old story worthless. The old story was a reasonable first draft, built from sound reasoning and honest limits, and much of it may still stand once the details settle. What the images do is not erase that draft, but deepen it, adding a chapter about a beginning more capable and more alive than we had allowed ourselves to expect. A first draft revised is not a first draft disproved. It is a first draft brought closer to the truth. There is a quiet humility in all of this, and a quiet joy as well. To have written a careful story of the early universe, and then to watch the universe hand back something even more generous than the story imagined, is not a defeat for science. It is science working exactly as it should. We guess, and we look, and the looking corrects the guess, and the corrected guess is better than the one before. The early galaxies are not a rebuke. They are a gift, an invitation to understand the beginning more fully than we could have from the timeline alone. They ask only that we hold our expectations a little more loosely and let the evidence lead, so we can lay the heavy word aside. The galaxies did not break the universe. They did not shatter any law or overturn any certainty about how matter and light and gravity behave. What they did was widen the story we tell about how it all began, pressing gently against the edges of the picture until the picture grew large enough to hold them. They took a timeline we had drawn with confidence and asked it, kindly, to make more room. And the universe, as it always has, remained exactly what it is, patient and lawful and far more interesting than any single story we could tell about it. The impossible, once again, was only the not yet understood, waiting quietly for us to catch up. And so we come to rest, where the question itself remains open. We have followed the young universe through its first surprises, and none of them have closed. We have looked out along light that has traveled almost the whole age of the cosmos, and we have found, at the far end of that journey, a beginning that does not match the patient story we once told. The images remain, and the puzzles remain within them, unhurried, waiting. It is worth gathering these findings together now, gently, the way one might lay smooth stones side by side, and holding them in view all at once before letting them settle. The first of these findings was simply presence. We pointed our newest eye at a stretch of time that was expected to be nearly empty, only a few 100 million years past the beginning, and we found the field already lit. There were more bright galaxies there than the old picture allowed, and each deeper look kept finding more of them rather than fewer. The dawn of the cosmos, it seemed, had arrived earlier than the story promised, and it had arrived shining. Before any question of shape or mass or age, there was this quiet fact to sit with. The early universe was already awake, already glowing, already there. Beyond brightness came the matter of mass, heavier and slower to explain. Some of these early galaxies appeared to hold as many stars as far larger, later galaxies, as though they had gathered the substance of a mature spiral in a fraction of the time the old timeline seemed to allow. To build so much so soon would ask for more mergers and more patience than the slow, bottom-up story had budgeted. The most extreme of them looked nearly as weighty as our own great pinwheel of stars, seen when the universe itself was very young. If those readings hold, then structure assembled with a speed the earlier account did not expect. Then there were the small red points of light, among the strangest things in all these pictures. Compact and intensely red, far more common than anyone had foreseen, they crowded the early images, like embers scattered across a dark floor. They might be dense knots of aged red stars, or the glow of gas falling toward a feeding black hole, or some quiet mixture of the two. Their redness could come from dust, from the age of their stars, from light stretched long by the expansion of space, or from all of these at once. Whatever they finally prove to be, they remain unresolved, small and calm-looking, and deeply puzzling, their nature still being worked out. Order, too, arrived ahead of its time. The story had expected the young cosmos to be a place of chaos, of clumpy and colliding and irregular galaxies, still learning their shapes. Instead, some of the early galaxies looked settled, turning as smooth disks, some already tracing the faint beginnings of spiral arms and central bars. These are features long thought to take billions of years to gather into place, and yet there they were, already turning in the young dark. If galaxies could calm into such order so early, then the violent, messy youth we had imagined was, at the very least, briefer and gentler than we thought. Stranger still was the early quad. Some of these galaxies had already stopped making new stars, gone reddened and still, finished with their brightest work while the universe itself was barely begun. To fall silent so soon, they must have formed their stars even earlier, in a fast and fierce burst, and then shut that making down. Their gas was spent, or driven out, or heated until it could no longer collapse into new light. They are the mirror image of the too bright and the too massive, not too young, but too old, too soon. Even stillness, it turned out, could come early to the young cosmos. And at the center of many of these galaxies sat the heaviest puzzle of all. Enormous black holes were already in place, anchoring galaxies that had scarcely had time to form around them. A black hole grown from a single collapsed star should not reach such a size so quickly, because there is a limit to how fast it can feed. Some of them appeared too large even for the galaxies that held them, the usual proportion between the two turned upside down. Perhaps they began from heavier seeds, from great clouds of gas that collapsed straight into massive beginnings, skipping the star entirely. However they grew, the giants at the centers of galaxies were already grown, and exactly how remains an open question. These, then, are the findings, laid side by side. Early brightness, early mass, the little red dots, early order, early quiet, and the early giant black holes. No single one of them would have unsettled the old story on its own, and each might yet be softened or explained away. Taken together, though, they form a single gentle pressure against the patient account, a sense that the young universe was faster and brighter and more fertile than the tidy version had drawn it. They lean in the same direction, all of them pointing toward a beginning that did more, and did it sooner, than we had thought to ask of it. And yet, alongside these findings, there are the calm ways the puzzle might soften, and these deserve to be held just as gently, for the answer, when it comes, may lie among them. Some of the easing may come from how we read the light itself. A handful of very bright, very young stars can outshine everything around them and lead the eye to count more mass than is truly there. The glow of a hidden black hole can swell a galaxy's apparent brightness, and here the small red dots return to remind us how easily light can mislead. Dust and reddening can confuse estimates built on color, and assuming an ordinary mix of stars can tip the counting upward. Patient confirmation has already lowered some of the boldest figures, and it may lower more. A portion of the impossibility may simply be the difficulty of reading faint light that has crossed almost the whole universe to reach us. The rest of the easing may come from the young universe itself, working differently than the one we know. Perhaps star formation was more efficient then, the gas denser, more of it turning into stars before being blown away. Perhaps a first generation of stars unlike any that shine today, very massive and very hot and very short-lived, lit the early cosmos with a swiftness we no longer see. Perhaps there was less of the feedback that slows the making of stars in galaxies now. The timeline itself may need only a loosening rather than a fracture. The same physics granted a slightly quicker start. The young universe may simply have been better and faster at making stars than the story assumed. And so we arrive at the honest shape of the matter, which is that nothing here is truly forbidden. This is a model meeting its edge, not a law being overturned. The word impossible is a gentle shorthand for something not yet understood, and the long history of looking at the sky is full of yesterday's impossibilities become today's ordinary understanding. Again and again, the things that once seemed to violate the order of the heavens turned out only to enlarge it, and the account grew wider to make room for them. The galaxies did not undo the universe. They widened the story we tell about how it began, and they left a doorway open where we had thought the wall was solid. What stays unresolved is not a wound, but an invitation, a place where the picture is still being drawn. There is a quiet comfort in a question left this open. It means the cosmos is larger than our account of it, and that there is still farther to see, still more to gather in. A finished story would leave nothing ahead of us, but an open one keeps the way forward lit, and there is ease in knowing the picture is not yet complete. The early galaxies are there in the images even now, patient and glowing, having waited billions of years for their light to arrive and willing to wait a little longer to be understood. They ask nothing of us tonight, but that we notice them softly and let the not knowing rest easy. To live at a moment able to look this far back toward the beginning is a rare and quiet privilege, and it asks for no hurry. So let the young universe stay lit in the mind, its first galaxies glowing at the edge of the oldest light, holding their unfinished questions gently in the dark. There is time enough for the answers, and none of it needs to be settled now. Rest here at the doorway, with the earliest galaxies shining patiently on the far side of almost forever. Sleep well, and good night.